So our last theorem that we are going to talk about is the maximum power transfer theorem. And this is the last theorem that we are going to talk about when we talk about DC circuits that have only sources and resistors. We talk about the maximum power transfer theorem. So when we are talking about the maximum power transfer theorem, we are just trying to see the conditions that are required for a power source to deliver maximum power to its load. So remember, the purpose of having a power source is so that it can supply power to a load. Then the load will do the useful work. That's basically the purpose of having a power supply. So in this case, we are saying we want to look at the conditions which help us to have maximum power from the source into the load. So when you are talking about a power source and the power transfer of power, we normally talk about the efficiency of the system in transferring power from the source to the load. And this is very critical in power generation and transmission of large quantities of power. In that case, we are more concerned about the efficiency. But in communication systems and control systems, we are more concerned about the amount of power that is available, right? The amount of power that is available from the transmitter to the receiver. So when we talk about maximum power transfer, in this case, we're trying to see the amount of power, not necessarily the efficiency, the amount of power that is delivered to the source, to the load by the source. So in efficiency, we are talking about the ratio of the output to the input. When talking about the amount, we are talking about quantifying the power that is transferred to the load. And that is our concern in the maximum power transfer theorem. Now, we have talked about Thevenin's equivalent circuit and Thevenin's theorem. And we realized that Thevenin's theorem helps us to convert a network into a simple power supply with a source and a resistor in series. And this can also be used in finding the maximum power in a linear bilateral circuit. That's why we had to do Thevenin's theorem first. But you realize that you can also find it in other forms. So that is our Thevenin's equivalent source, V Thevenin and R Thevenin. Then we have our terminals, and then the load is connected across the terminals to give us the terminal behavior. Now the power delivered to the load is equal to I squared RL, where I squared is the current and RL is the value of the resistance of the load. And if you were to evaluate I, in this situation, you realize that the value of I is equal to V Thevenin over the sum of R Thevenin and RL. That will be the value of the current that flows when the load is connected. And so we can say power is equal to this expression, V Thevenin over R Thevenin plus RL squared multiplied by RL, right? Then we are now saying there is a variation in the power delivered to the load as R error changes. Right? So we said our power will be equal to V Thevenin over R Thevenin plus R error squared multiplied by R error. So we are saying, as we change the value of R error, we are also changing the value of the power delivered. So if you check it closely, since there's a squared term here, it means there's a value whereby as R error becomes smaller and smaller, right? The power delivered also becomes smaller and smaller. We are looking at R error varying, right? Then, if R error is 0, when there is no load, there's no power being delivered, and we are at this point. If we start increasing R error, the value of the power will increase to this final value, which is P max. But then, when the value of R error continues to increase, now the ratio of R error over R Thevenin plus R error, this ratio, as R error increases, right? There comes a time when this value starts to decrease, because it will start approaching R error over R error, which is 1. Meaning to say, when R error becomes too large compared to R Thevenin, this ratio approaches 1, and then it will almost equal to V Thevenin squared, right? So the power will also start to decrease. Our maximum power transfer occurs at this point, and this value, it has been shown that the maximum power transfer occurs when R Thevenin and R load are the same. That is when R error is equal to R Thevenin. That is the point where we expect maximum power transfer. So if you want to state the theorem, you say that maximum power is transferred to the load when the load resistance is equal to Thevenin's equivalent resistance as seen from the load or from the terminals where the load is connected. So R error should be equal to R Thevenin. And if that is the case, that is the proof. You don't need to prove it, right? You don't need to prove it. But it can be shown that this happens when R Thevenin is equal to R error, where we get maximum power transfer. Don't worry about the proof, right? So what it now means is that at the condition of maximum power transfer, the maximum power will become V Thevenin squared over 4R Thevenin, right? Your mathematics, it tells you that V Thevenin squared over R Thevenin plus R Thevenin squared multiplied by R Thevenin. We said that occurs when R is equal to R Thevenin. So this becomes 4 R Thevenin squared, and then it will cancel out with that to give you this expression. So this is the expression for maximum power transfer. So we say maximum power transfer occurs when R Thevenin is called the load, and then what it means is the power will be given by this expression, V Thevenin squared over 4R Thevenin. And hence, what you need in your transmitter or in any circuit is to match your load to the internal resistance of the source if you want to transfer maximum power, right? When you want to transfer maximum power. For example, The variable resistor in the circuit below is adjusted for maximum power. Find the value of RL and the maximum power. Now, you know that maximum power transfer occurs when your RL is equal to R Thevenin. So your first point of call is to find R Thevenin, because that is only where RL will get maximum power. So in finding R Thevenin, we don't have to revise so much. We remove the sources and we put our resistors, and we find the resistance from the load. Remember, when you're finding R Thevenin, we remove the load and then we have our resistors. So this is 6K, this is 10K, this is 1.25K. So 1K25, it means 1.25 kilo ohms, right? Then you find your R Thevenin. First, you see that your 6 will be in parallel with your, so I can say R1T will be 6 times 10 over 16 kilo ohms. It is about 60 over 16 kilo ohms, right? And you get your 15 over 4 kilo ohms. I can leave it like that. Then my new circuit will be 15 over 4 kilo ohms in series with 1.25 kilo ohms. And my terminals A and B, where I've removed my source, will give me R Thevenin. Remember, this will be a bit faster because we did it before, right? So that is where we are going. Then after finding Thevenin's equivalent resistance, then the next thing, you will know that variable resistance that you want will be equal to R Thevenin. I think you can do that. You can do that on your own. Then, let me see if I can get the correct answer easily. So 15 over 4, that's 3.75 plus 1.25 kilo ohms. That becomes my R Thevenin, which is got my 5 kilo ohms as you get it on the screen, right? Then the question says, find the value of RL and the maximum power. So for maximum power transfer, already we say RL is got R Thevenin, which means our RL is 5 kilo ohms. That's what we require. Then find the maximum power. Now, the maximum power now, it comes from finding first the voltage, Thevenin's equivalent voltage, and then reconnecting the load and finding the power through the load. We have two sources, so we use superposition theorem or source transformation, whichever you want. For today, let's use source transformation since someone wanted to use source transformation. So the 8-volt source and the 6 kilo ohm resistor will give us 18 over 3, will give, 6 will give us 3 milliamps. Then it's in parallel with 6 kilo ohms. Then it also is in parallel with 5 milliamps and 10 kilo ohms. Then in series with 1.25 kilo ohms. And to get our terminals, we want to find V Thevenin at the terminals. I hope you are following. I'm not showing you my equating so that you also calculate with me. Then you get the actual answer. So we combine those sources, they give us an 8 milliamp current source. Then we have 6 in parallel with 10. We got 15 over 4. So now we have 15 over 4 kilo ohms. Then we have 1.25 kilo ohms. And we have our terminals to get Thevenin, right? Then after that, remember we said Thevenin is the open circuit voltage across terminals A and B. So if it is the voltage across terminal A and B, 1.25 kilo ohm resistor, the current is called 0, so it's out. So the voltage will be the current, the voltage across the 15 over 4 kilo ohm resistor. So our Thevenin becomes equal to 8 times 15 over 4, and we get our 30 volts. I hope it comes out well. We get our 30 volts. I want it to be working there. I'll show you the answer once. That is our Thevenin. So we go back and we have our 30 volt source with an Thevenin of 5 kilo ohms at maximum power transfer. We have our 5 kilo ohms, right? And the power that we need will be P max, which is equal to Thevenin squared, which is equal to 30 squared. Then we have 4 times 5, which is our Thevenin squared, right? And we are getting 30 squared, that's 900 over 20. This is 900 volts over 20. This will be kilo ohms per se. So we'll just say 900 over 20. But then we have voltage in units and resistance in kilos. So our power will be in milliwatts. So we have 900 volts squared over 20 kilo, right? And we have 45 milliwatts as our power transferred, right? That will be our power transferred. Okay, so let me change the setup slightly so that you can see how we're calculating these values. How we're calculating these values, right? Okay. Let me show you what I have here. So our starting point, we said, since we want to get the value of the resistance when there is maximum power transfer, we know that the value is maximum when the value of the load is equal to the value of Thevenin. So we want to calculate Thevenin first. So we removed the voltage source here, right? And we removed the current source there. We are left with our 3 resistors. Then we notice that the 6 and the 10 are in parallel. They give us 15 over 4 kilo ohms. Then the 15 over 4, which is in this side, goes in series with the 1.25, and we get our 5 kilo ohms as our R Thevenin. Everyone should have got that. Then the next thing that we want is, we know that the maximum power transfer occurs when we have the load and the R Thevenin being equal, and we want to find the value of Thevenin's equivalent voltage. And today I have not employed superposition. I used the source transformation. So this was the 18 volt source and the 6 kilo ohm in series. I converted them to a current source. They give me 3 milliamps and 6 kilo ohms in parallel. Then I combine the two current sources in the facing the same direction. It becomes an 8 milliamp source in parallel with a 15/4 kilo ohm resistor. And then that circuit is in series with 1.25 kilo ohms. Now I want to find the voltage on this side. So I is equal to 0 for this resistor, so we don't consider it. So our loop will be just this loop. And then the current here is also the current there. In the end, that is the voltage across that resistor is also our Thevenin's equivalent voltage, which comes out as 30 volts. After that, we redraw our Thevenin's equivalent circuit. So this is Thevenin's equivalent circuit, which I have just put in the highlighted zone. That's our equivalent circuit, and we reconnect our load to make our calculations. And we know that at maximum power transfer is V Thevenin squared over 4 R Thevenin, and the end we get our 45 milliwatts as the power transferred under those conditions, right? I'm sure this is very, very clear. Then we go on to the next example. This example, I'll just show you the example. You work it out. Since you are coming back to show me your working later. Okay? But for the time being, let's look at the example. So this is what we're talking about. Then the next one, the load resistance in the circuit below is adjusted until maximum power is delivered. Find the power delivered to the load and the value of RL. So what you have to do is notice the section where we have to find Thevenin's equivalent circuit, right? So it means our load is here. So this becomes our terminal A and terminal B, right? Then after that, we have this current source and the voltage source, and also our resistors there. Now, what we want to do is to calculate the voltage across A and B, and also RL with respect to that. So, as usual, our first point of call is to remove the sources and redraw our circuit without the sources. So we have a 1 kilo ohm, right? We have 500 ohms. We have 1 kilo ohm, right? And then we have our terminals A and B like that. Because we have removed the current source there, we've also removed the voltage source there. So that is your circuit that you will use to calculate Thevenin's equivalent resistance, R Thevenin. This is the value to which the load was adjusted. So that is your new circuit. Voltage source removed, current source removed, and you are left with that combination. And so you will see that it will be 1.5 kilo ohms in parallel with 1 kilo. right? 1.5 kilo in parallel with 1 kilo for a start. So R Thevenin will be equal to 1.5 kilo in parallel with 1 kilo. So that will be 1.5 times 1 over 2.5 kilo ohms, right? And you simplify that, you'll be having 1,500 over 2,500, right? You get your 3 into that, 5 into that, you get your 3, 5 into that, you get your 5. 3 over 5, which is called 0.6 kilo ohms, which is called 600 ohms. That's the equivalent resistance, 600 ohms. I know the issue now comes on Thevenin's equivalent voltage. At Thevenin, I'm sure no one has a problem with that, because it's simple after removing the sources. Now, source conversions will not work because we don't have a source that is in series or in parallel with the resistors. So we consider, say, when we consider the 10-volt source, we remove the current source. Then we have our values as usual. We have our Thevenin, right? So in that case, Thevenin 1, let's say Thevenin V, because it's according to the voltage source, will be equal to 10 volts, because that's an open circuit which comes out. Since we have removed that, what we measure is the source. So for the voltage source, it's equal to 10 straight away. Because you combine that and the that, there's no current flowing in the circuit, so there's no voltage drop across any of the resistors. So that is what you get. Then using the 2 milliamp source, but here you should know that A is positive. Since we are using superposition, A is positive. Then for the source, we short circuit that, removing the voltage source. And then we have our 2 milliamps going that direction. These combined, and we have our Thevenin due to the current source, we can say Thevenin C. Right. Now, in that section, you have to see that there is no current flowing to the terminals A and B, because we are dealing with the open circuit voltage, right? Since we are dealing with the open circuit voltage, our currents will be flowing in different loops. So in other words, the current, let me find another color so that when I show you, we'll see the difference. Right, so our currents will come like this, branches into those two portions, right? Then it will come back through that loop, right? So according to this circuit, we have to determine where exactly are we measuring the V Thevenin. Because in that case, it's a bit tricky, right? A and B, 1 kilo, 1.5 kilo. So I was saying the current is flowing out of the source. There's no branching. It follows the path here. At this point, it branches into I1 and I2. And then I1 is also flowing through 1 kilo. So the first thing that we have to do is find I1 and I2. So I1 becomes equal to 500 over 2,500. Well, that side, the two resistors are now in series with respect to the current, multiplied by 2 milliamps, right? And we get 1 over 5, which is equal to 0.2 times 0.2 times 2, you get 0.4 milliamps. That means the current through I2 becomes equal to 2 minus that, which is 1.6 milliamps, right? Then we are measuring the voltage between those 2 points. We are measuring now the voltage between A and B. I will show you what I'm doing here so that you see how to reorient yourself. Okay? You see how to reorient yourself. So when you are measuring the voltage now across A and across A and B, sorry. What you are really measuring is the voltage drop across the 1 kilo ohm resistor at the top. Let me redraw and show you why. You could put that source, no connection there. Then this point is also A, right? Then this resistor is coming there to connect to the source. And that point is our A. So the voltage across A and B is just the voltage across those 2 points. The voltage across this point is also B in that. And so what will be the voltage drop across those 2 points will be the drop across 1 kilo ohm resistor. And that drop will be 0.4 times 1, which is got 4 volts. And in that case, A is negative. Then V Thevenin now will be equal to the result of the voltage source and the current source, which in our case is 10 minus 4, which gives us 6 volts. Well, I have to cross-check because I'm not having a calculator here. Then what will be the maximum power transferred? Should be 36 over R Thevenin. Is that correct? 36 over 4 R Thevenin, that's 2.4 don't know if I didn't get my working wrong. That's 9. That's 6. Is that correct? I think I have to recheck my calculations with a calculator to see if I didn't give a wrong value somewhere. But that is the way it should come out. Anyway, my time is almost up. So I'll stop this. Then maybe we wait for about 10 minutes or so. Then we do that revision of the question. That will be our last example. So in the next discussion, I'll be showing you the working, which I was explaining to you. But remember, that will not be recorded because it will be a simple discussion. Okay? So I think we are now fine. It's 12:35. Let's say it's 12:45. We'll come back and make a discussion. Also try to do your working on that. I will show you what I was presenting here. Let's wait for now.